Thank you for the introduction, and I'd like to thank the organizer for this kind invitation. And during this talk, I will always assume that our base field is complex numbers. And we will recall several notions in algebraic geometry. Let V be a vector space of dimension n plus 1, and let V star is the dual space of V. Then let us consider a group action of C star on V sending t, x0 to xn to tx0 to txn. And if we take the quotient of V by this group C star, let me extract the origin of this vector space. Then let us denote this space by PV, and it is of dimension n. So sometimes we will denote it by P sub n. And P sub n star is by definition P of V star. So these two are the main objects of this talk. And this space is called the projective space of dimension n. This is called the dual projective space. And the remark, first, this first projective space Pn parameterizes one-dimensional vector subspace of V, and secondly, the dual space, which is PV star, parameterizes one-dimensional vector subspace of V star, which means it parameterizes n-dimensional vector subspace of V. Now, let X be a smooth algebraic variety. And again, it is always over complex numbers. And for example, our X can be the projective space of dimension n, or the product of two projective spaces, and so on. And now, let us define the vector bundle. E is called the vector bundle of rank R on this algebraic variety X if it admits a surjection P from E to X such that first P is a linear fibration, secondly it is locally trivial. So for example, first example of, before giving several examples, let us remark that we can define the tensor product or direct sum or dual space, dual vector bundles of a given vector bundle E. And as examples, first example can be the tangent bundle on projective space. And secondly, the tautological bundle. Bundle on Pn, which will be denoted by OPn minus 1. And as we remarked before, we can define tensor product on the vector bundles and the dual vector bundles. So from this, we can define OPn k for arbitrary k in integer numbers. And the first theorem, which is the most important and fundamental in studying vector bundles on algebraic variety due to Grothendieck, is that if E is of
K is positive real number, you are taking dual of this OP minus 1 or?
yes, so for example, OPn1 is defined to be a dual vector bundle of this. And if E is a vector bundle of rank R on P1 when n is equal to 1, then E is a direct sum of line bundles. And for our convenience, we will always assume that these AIs, which are integers, are ordered in a decreasing, will be in decreasing order. So this is the theorem due to Grothendieck. And now, let us assume that, again, E is a vector bundle of rank R on X. And the definition for the stability is as follows.
E is, this is just a topological complex vector bundle, right?
Holomorphic vector bundles. So everything here is holomorphic over C.
Locally triviality. Holomorphic triviality.
Tangent bundle shows holomorphic tangent.
Okay.
Yeah.
Because otherwise, this topological is trivial, why Grothendieck is. Okay.
Yeah. And E is called stable if we have the following inequality. For all subshifts f of E, if we have this inequality as polynomials, then E is called stable. And to define this Euler characteristic, we have to fix an ample line bundle. So in this definition, the choice of fixed ample line bundle is hidden. So this is our definition for the stability. And the next theorem due to Maruyama is that there exists a moduli space M, H, R, C1 to CR of stable vector bundles of rank R on X with the Chern classes C1 to CR. If we fix the rank and the Chern classes, and with respect to a fixed ample line bundle, then we have a moduli space which parameterizes all the stable vector bundles with this numeric invariance as a quasi-projective algebraic variety. This is the theorem due to Maruyama. And the reason why we have this stability condition to construct such a moduli space can be observed by the following examples. First, let us consider the family of the following vector bundles of rank 2. And secondly, the fact is that there exists a C parameterization of rank 2 vector bundles on P1 such that ET is isomorphic to OP1, direct sum with OP1, when T is not equal to 0, and E0 is isomorphic to OP1 K, direct sum with OP1 minus K, where K is not equal to 0. So if you choose one integer K which is not 0, then we can construct C's parameterization ET which have these two conditions. So from these two examples, we can recognize that this family cannot be algebraic variety, and this family in this family, this point in the moduli space, if there is such a moduli space, then this point cannot be a closed point because of this condition. So if we consider an arbitrary family of vector bundles, then it does not give us a nice moduli space in terms of a functor representation. So we need some restriction on our family of vector bundles. And the one thing they recognize is that the reason why we cannot construct a moduli space from these two examples is that the degree, we don't have any control on the degree of the sub-bundles of this rank 2 vector bundles. So here, we can have arbitrary large degree on these sub-bundles. And also, we have this sub-bundle. So in this definition, somehow we have some control, or we have some bound on the numeric invariance of the sub-bundle or sub-shapes of given vector bundles. So this
I feel quite unstable with the stability. So could you give me some geometric meaning of this stability of vector bundle itself?
Geometric meaning of this?
Yeah. What does this mean?
So for example, let us assume that the dimension of x is equal to 1. So x is a curve. Then this condition is same as the degree of f. This is just this stability condition is same as this. And this is exactly what I was trying to tell from these examples.
What do you mean by degree of that?
So on curves, so f is a line bundle on curves. So we have line bundle can be corresponding to a divisor. So we have a natural degree notions. Yeah. So the main theme of in our research is to study the geometry of this moduli space. So for example, what is the birational property of this moduli space? Or concretely, what is the explicit description of such moduli space? That is our main goal. Since we have a complete answer in the case of P1, the next case is when n is equal to 2, the projective plane. So let us assume that E is again a vector bundle of rank R on P2, and let L be a line on P2. So L is an element, L is a point in the dual P2. Then, by the theorem due to Grothendieck, we have the following decomposition. So E, if we restrict E to L, then this vector bundle on L can be a direct sum of line bundles. Again, we will put AIs in a decreasing order. Then let us denote by A sub E comma L these R tuples. Then let us define A sub E to be the infimum of this A sub E comma L when L is a point in the P2 dual space. So here, when we take the infimum, we take the natural lexicographic order in these R tuples. Then we can naturally define the notion of jumping lines. Define L, a line on P2 is called the jumping line of E if A sub E is not equal to A sub E comma L.
So you have this splitting by Grothendieck.
Yes. And let us denote by S of E the set of jumping lines. And the theorem due to Grauert, Mulich tells us when E is a stable vector bundle of rank R on P2, then we have AI minus AI plus 1 is less than or equal to 1 for all I, where AIs are the numbers in AE. So what does this theorem mean? So for example, let E be an element in this moduli space. So which means E is a stable vector bundle on P2 of rank 2 with first chunk class 0, second chunk class K. Then, since E is of rank 2, if we restrict to L, then we have the following decomposition. And since the first chain class of E is 0, we have A1 plus A2 equals 0. And if L is general, if L is general means L is not a jumping line, then from this Grout-Millet theorem, we have A1 minus A2 is less than or equal to 1, which means with this equality, we have A1 is equal to A2 is equal to 0. So which means for general line L on P2, if we restrict the vector bundle to this line L, then we have a decomposition OL plus OL. So L is a jumping line of E if and only if H0 of E twist by -1 restrict to L is not equal to 0. Now, using this criterion, H0 is the global sections of this vector bundle.
Global section?
Yes.
Non-zero section? Non-zero section or just a global section? Okay.
Yeah.
It may have zero points.
Yes, yes. And with this criterion, Barth gave us the following theorem, Theorem 4, due to Barth. For general vector bundle, E in the moduli space M to 0K, S of E, the set of jumping lines, which is a subset of P2 dual, is a smooth curve of degree K. So, for example, when K is equal to 2, M2, 0, 2, we have a map from this moduli space to P5, which is OP2 dual space 2, sending E to the set of jumping lines. Because this map is well defined due to this theorem 4, because when K is equal to 2, the set of jumping lines form a smooth curve of degree 2, which is a conic on P2 dual space. And in this case, this map is an injection. And in fact, we can...
Why is OP2 is P5?
This...
What is this? Absolute
So OP2 dual parenthesis 2 is a parametrization, is a line bundle, the corresponding to all the conics on P2 dual space, and we take the projectivization. So I mean, this is the quadratic equations on P2 dual space, and then take the projectivization, so it will be the family of all the conics in P2 dual. And in fact, this moduli space is isomorphic to this P5 minus V3, where V3 is the second variety of the Veronese surface S in P5. I mean, obviously, the image of this map lies in this space because Bernoulli surface, each point in this Bernoulli surface corresponds to a conic of rank 2. Is it rank? I mean, each point on this Bernoulli surface corresponds to the double line. And V3, which is the second variety of this Bernoulli surface, corresponds to the double lines. And if you take the subtraction by V3, then all the point in this algebraic variety corresponds to smooth conic. And in fact, in this example, what I'm trying to tell is that this map is actually an isomorphism between this moduli space and the whole family of smooth conic. And now, so the natural generalization is that what happened if we restrict E to conics? Klaus-Hulig investigate the vector bundle E restricted to a double lines L square to study the moduli space of vector bundles of rank 2 with odd first-hand class. And for example, he showed that M2 minus 1, 2 is isomorphic to this cubic 4, 4 minus Bernoulli surface using this restriction to the double lines. And there are also several attempts to study the certain moduli space of vector bundles by restricting the vector bundles to two lines or smooth conics.
I have a very stupid question. Can you possibly then have some kind of stratification of P5 in terms of those moduli spaces?
You mean naturally?
I mean, I'm just curious because it looks like P5 is going to...
Actually, right after I recognized these two results, my first attempt to answer to your question, but I couldn't find the natural stratification. But it seems there is not. Yeah.
Is there a way to see the Bernoulli surface as some kind of moduli space or some rank, whatever effect? Because just out of curiosity, I'm just asking. So if there is nothing known,
it is not a moduli space of certain vector bundles, but there is a mapping from certain moduli space of not vector bundles, non-locally free shapes to the Bernoulli surface. For example, what we can recognize from this example is that the set of vector bundle does not form a proper, compact algebraic variety. So somehow we need a natural compactification. The natural way is to put the non-locally free shapes. So for example,
when Maruyama's result says there's a moduli space, what does he mean by moduli space? Does it have any structure?
It is a quasi-projective algebraic variety.
Quasi-projective.
And it is a nice property in terms of a functor representation. So in general, it is not a fine moduli space. In general, it is a coarse moduli space. But in some case, it is a fine.
So generally, it is a quasi-projective space.
Yes. For example, M bar 2 minus 1, 2, which is the moduli space of all the stable sheaves of given numeric invariant, then we have a natural map from this to V3. So inside this moduli space, the locally free sheaves part can map to V3 minus S, and all the non-locally free sheaves can map to the Veronese surface. But the problem is that it is not one-to-one. In fact, it has a P1 fiber. So I don't see any moduli space which corresponds to the point on S, one-to-one. Actually, this is one of the work in my thesis. In fact, this is a proper transform from V3 with respect to the blow-up of S, blow-up of P5 along S. So V3, this cubic fourfold, is singular on this Veronese surface. So if you take the blow-up of P5 along this Veronese surface and take the proper transform of V3, and it is smooth. And in fact, this proper transform is isomorphic to this convectification. And thirdly, we will discuss a smooth quadric case. Now let Q be a product of P1, two P1s, and it is embedded into P3 by staggered embedding. And we can consider two projections, P1 and P1. Let us denote the first P1 by PV1 and second one by PV2, where V1, V2 are two vector spaces of dimension 2. And let us denote the first projection by pi1 and pi2. And as notations, we will define OAB to be pi1 pullback or P1A tensor with pi2 dual pullback or P1B. And for E, a vector bundle of rank R on Q, then we will denote by E A comma B, E tensor O A B. This is quite conventional notation. And let CH to be a curve which is an intersection of H with Q, where H is a hyperplane section in P3. So this is a projected plane in P3. So this is an element in P3 dual. And we will assume that CH is smooth, which means H, this projected plane, is now a tangent plane to this quadric Q. Then, if we choose an isomorphism from P1 to this smooth quadric, a smooth cone, then we have the following decomposition. If E is again a vector bundle of rank R on Q, then if you take the pullback along F, then we have OP1, OP1 AR, again due to Grothendieck. Again, we will put AIs in a decreasing order. Then, similarly, we can define jumping conics.
CH is rational code.
Yes. It's conic. And we will define A sub E comma H to be these numbers, A1 to AR. And A sub E to be, again, the infimum of A sub E comma H, where H is P3 dual, where we assume that H is general, because C sub H is not smooth, and this R tuple cannot be defined. Now, the theorem phi tells us the same kind of ground-to-multi theorem. So if E is stable of rank R on Q, where since we use the notion of stability, we have to fix an ample line bundle. Here we always assume that our ample line bundle is OQ11, which defines an embedding of this quadric to P3. Then we have AI minus AI plus 1 is less than or equal to 1 for all I, where AE is A1 to AR. This is the same form of the ground-to-multi theorem on the projective plane case, but this theorem is not obvious because from the result, well-known result by ground-to-multi and Spindler and Maruyama, since the degree of this quadric is 2, the natural bound for this number should be 2, but in fact it is 1. Now,
If we use different kinds of embedding other than the singular embedding, do we have similar result?
actually, yeah, we can think about the problem, but I have not thought of it yet, but yeah, this is also quite an interesting question. Let M of K to be the moduli space with respect to this ample line bundle 2 minus 1 K. So here rank is 2, first chain class is by degree minus 1, second chain class is K. If E is an element in this moduli space, then as before, A sub E is equal to -1, -1. This is A sub 1, this is A sub 2. So which means if we restrict this vector bundle E to the general conic in this quadric, then if you take the pullback, then we have OP1, -1, sum with OP1, -1. This is what it says. And so from this, we can recognize that the conic CH is a jumping conic. Did I define jumping conics? Oh, no. So here, CH is a jumping conic of E if A sub E is not equal to A sub E comma H. And CH is a jumping conic of E in this moduli space M of K if and only if H0 of E restrict to CH is not equal to 0. So in this case, it is 0. And using this criterion, not yet. Yeah. Before using this criterion, let us define the following set. As before, let us define S of E to be the set of hyperplane section such that H0 of E restrict to CH is not 0. So one of the reasons why we use this criterion is that here, in this case, the definition of jumping conic is not proper, which means if you use this definition, the set of jumping conic is not a proper algebraic variety. But if you use this cohomological criterion, now S of E is proper. Now, theorem 6 is that if E is an element in this moduli space, then E is the cohomology ship of the following monad here 0 to K11 tensor with O minus 1 minus 1 to K10 tensor with O negative 1 0 direct sum with K01 tensor with O 0 negative 1 to K00 tensor with O 2 0 where Kij is H1 first cohomology of E twist by negative I, comma negative J. So this is monad, meaning the first map is injection, second map is surjection. So this is an exact sequence except the middle one, except at the middle point. And this E is a cohomology of this monad, means E is isomorphic to the kernel of this surjection by image of this first injection. This is quite routine. In this theorem, really standard method was used. For example, if you take you consider the product of two quadric and consider the diagonal, and then consider the causal complex associated to this diagonal, and then take the Rayleigh spectral sequence, and after using the stability condition of E, then we will get this cohomology ship. And now, from this monad, we can define simple looking map, delta, from V1 dual tensor with V2 dual to homomorphism group from K11 to K00, where again V1, V2, actually I already erased, but Q is isomorphic to P1, P V1 product with P V2. And these are the dual space of this tensor product. And from the sequence, so if we consider the sequence E negative 1 to E restrict to CH, and then take the long exact sequence of cohomology, then H0 of E is 0 because of the stability condition. So we have H0 E restrict to CH to H1 of this, which is by definition K11, and H1 of E is by definition K00. And here, this map can be checked to be this map, delta of G, where Z is a coordinate defining this hyperplane section. So, this is not equal to 0 if and only if the determinant of this matrix is equal to 0. So the theorem, corollary is that S of E as a subset of P3 dual space is a hyperplane, a hypersurface of P3 dual space of degree And in fact, you can easily compute that the dimension of these two vector space is k minus 1, where k is the second Chern class of this vector bundle of degree k minus 1. Now, so since we have several theorems, the final thing we have to do is to see some examples. Let us assume that k is equal to 3. So if E is a stable vector bundle in this moduli space with second Chern class 3, then from the corollary 7, S of E is a hypersurface in P3 dual space of degree 2. And in fact, we can prove that it is a quadric cone. And our vertex point, let us denote this vertex point by H. And our vertex point is a point in P3 dual space. So which means H is a hyperplane section in P3, in our original P3. Now consider a map from M3 to P3 dual space, sending E to the vertex point of S of E. Then fix hyperplane section H in P3 dual. Then we can easily check the H0 of E11 is equal to 2. And if E is an element in the preimage of H, then we have the following exact sequence. Where this Z is a zero cycle whose supports is on Z, is on H of length 3 because of the second Chern class of E. So from this, we can consider a diagram as follows. Here we have the preimage of this vertex point H, and consider P2 bundle, which is P of U, over CH3. Where CH3 is a Hilbert scheme of zero cycles of length 3 whose support lies on CH. And as we assume that H is general, means C sub H is a rational curve. So CH is isomorphic to P1, and the Hilbert scheme of length 3, zero cycles on P1 is isomorphic to P3. And P of U over this P3 is a P2 bundle over this P3 whose fiber is P projectivization of x1 iz11 O, which parameterizes this extension. This extension is parameterized by x1 of this comma this. And this can be checked to be isomorphic to P, H0, OG duo. This is the Stokes skyscraper shapes over Z. And this is isomorphic to P2 because of the length of Z. So from this isomorphism, we have a natural coordinate on this P2 with respect to the point of Z. Now, again, now consider a map from here to P5. Here, this pre-image element in this pre-image is a vector bundle E, and we have a map from here to P3 dual. So for this E, S of E is a quadricon with the vertex point P, a vertex point H, and then if we take the project from this vertex point, then we have a conic, smooth conic in P2. P2 dual. So we send E to the projection from H to P2, and then we take the image of this quadricon. So this projection, the image of this projection is a smooth conic in P2 dual space. This is again P5. And we have a natural map from here to here. Now, the proposition A is that what is this map? So to see what this map is, we can check the fiber. What is the map? What is the restriction of this map to the fiber? And the fiber is this P2. So the proposition A tells us that the map from this fiber P2, P x to 1, 2, this P5 is given by here, as I said before, this is a natural coordinate system with respect to this Z. So C1, C2, C3. This is the coordinate from the point G1. This is from G2. This is from G3. And this point maps to a certain quadric equations. And this quadric equation is given by C1, Z2, Z3. G2 equals 0 is a dual line corresponding to this point in P2, plus C2, Z3, G1, plus Z3, G1, Z2. So this is the proposition A. And this proposition seems to be really natural, but the proof is quite complicated, and this is the hardest part. Now, let V be the, let us denote this map by F, and let V be the closure of that map, the closure of the image of that map. If V is a general element in this image, which means V is a quadric equation on P2 dual space, then from this proposition we can tell that V is a Poncelet related to the dual conic of CH, which means in our original space P2 we have C sub H. Here P2 is our hyperplane section, and hyperplane section intersect with our original quadric Q along this smooth quadric CH, smooth conic CH, and then consider the dual plane, and you take the dual conic of CH, so V is a general element in this image V, meaning V can be expressed by this equation for a certain G1, G2, G3, which means there exist 3 points on this P2 dual whose lines connecting each other are tangent to this dual conic, and our V passing through these 3 intersection points. This is the definition of the Poncelet relation. And it is a classical result that this Poncelet relation has a P1 fiber, which means the image V, the map from here to here, has P1 fiber. And this is dimension 4. And it is from the deformation theory, it can be easily checked that the dimension of this fiber, this pre-image, is also 4. So from this map is injection. So theorem 9 is that the map from H to P5 is injection. In fact, the set of functionally related conic forms a hyperplane section in this P5. So we have the following theorem. In fact, there should be a lemma. Theorem 10. There exists the moduli space M3 admits 5-ration M3 to P3 dual space whose fiber is an open Zariski subset of P4. So as a corollary, this is birationally equivalent to the product of P3 and P4. So we have this theorem, and in particular, that map is injection means our jumping conic, the set of jumping conic S of E, determines uniquely our original vector bundle E in M of 3. So which means we have all the information to characterize E inside this set of jumping conics. And in fact, this fact is also true when K is equal to 2. And we have also really nice, beautiful geometry in the case of K is equal to 2. Okay, I think this is the end.